Hi, my name is Bob and I'm with my teammate Tanmay. We are here to present our project on supporting electric vehicle planning in African cities as part of data science for common good. I'm a PhD student in the ECE department and Tanmay is a master's student at the CICS. This work is in collaboration with the World Resources Institute, a global research organization that works on development issues that range from food security to energy and climate change. We also thank StimaLab for providing us with invaluable domain expertise and resources. As many of us know, internal combustion engine vehicles are responsible for a large chunk of global greenhouse gas emissions. We see from the graph that vehicle emissions account for more than 70% of global transport sector emissions. To combat this, governments all over the world are instituting targets and policies that encourage adoption of EVs. Widespread adoption of EVs, however, still faces a host of challenges. For starters, while EV technology has improved tremendously over the years, there needs to be a large-scale deployment of infrastructure such as charging stations, electric grid reinforcement, and updating of policies, all of which require actionable information about the vehicle purchases and usage patterns. For developing countries, the challenges are even greater. This is because there is not enough data on the transportation sector, which is necessary to plan the deployment of EV infrastructure. This is where our project comes in. In this project, we use deep learning models to detect and count vehicles in Nairobi from publicly available high-resolution satellite imagery. In order to build our model, we relied on two publicly available datasets. The first is a set of overhead imagery from 6 cities from developed countries. This car overhead with context dataset has a resolution of 15 centimeters per pixel and contains more than 30,000 car annotations. The second dataset consists of thousands of satellite images taken over Nairobi. These images have a resolution of 30 to 50 centimeters per pixel. We manually annotate about 6,000 cars on these images.
We run multiple experiments with different approaches, a purely image classification based and a standard object detection pipeline. Both the approaches require some manual data transformation and engineering tricks to work, and they also have different pros and cons. First, we reduce our task into an image classification problem. We do that by slicing the large image into multiple smaller ones, such that no slice has more than 9 cars in it. We then train a popular convolutional neural network architecture called ResNet 50 to learn and classify these images from 0 to 9. And then we combine these counts over the whole image and visualize the results in form of an overlay on the full-sized image, where each box shows us the vehicle count on it, as shown in this image. Unfortunately, this model does not perform well on African cities due to low resolution data and a wide variety of unseen artifacts in the images that are a function of the less urban setting. For the object detection approach, we use a popular detector called YOLO that combines classification and regression techniques to inform us about the location of each instance of the car in the global context of that image. And it can do it virtually in real time. Our detection model looks at each instance of the car in a global context and outputs a tight bounding box with the confidence values. The results of our detection model translate well onto our lower resolution satellite images of Nairobi, and we achieve close to 90% accuracies on these datasets, while processing 18 square kilometers of region in a minute. We faced some challenges during this project, primarily due to the nature of the datasets available. We had to downsample the images from our COWC dataset, which understandably comes with a decrease in accuracy. Moreover, our dataset did not come with bounding box annotations required to train it using a standard YOLO pipeline. So we had to approximate the box sizes using the centroids of each car. To summarize, we hand over a deep learning model that looks at high resolution overhead satellite images of a city and informs us of the vehicle usage and density in that area. And the model has a fast enough inference time that it can easily be integrated onto a visualization dashboard. Thank you.